Mastering Node.js Streams, a deep dive for the technical interview. Introduction. The why of streams beyond a simple I/O abstraction. At its core, the Node.js stream module is a fundamental abstraction for handling streaming data. It represents Node.js's elegant solution to two primary constraints in computing: finite memory and the inherent latency of input-output I/O operations. Traditional data handling often follows a read-all-then-process model, where an entire data source, such as a large file, must be loaded into memory before any processing can begin. This approach is not only inefficient, but can be catastrophic for server stability, as a file larger than the available RAM will cause the application to crash. Streams invert this paradigm. Instead of loading everything at once, they process data sequentially in manageable pieces, or chunks. This chunk-based processing is the foundation of their efficiency. Conceptually, a stream can be visualized as a conveyor belt or a water tap. Data flows continuously over time rather than arriving in a single, monolithic block. This approach provides two major advantages: memory efficiency, as you never need to hold the entire dataset in memory, and time efficiency, as you can begin processing data as soon as the first chunk arrives, rather than waiting for the entire payload. This design is not merely an optimization, it is a direct manifestation of Node.js's core philosophy of non-blocking, event-driven I/O. The stream is an abstract interface, not a concrete data structure, and virtually all of Node.js's core I/O-bound modules are built upon it. Modules like FS for file system operations, HTTP for network requests, Net for TCP sockets, and zlib for compression are all implementations of the stream interface. For instance, in an HTTP server, the incoming request object is a readable stream, and the outgoing response object is a writable stream, allowing developers to efficiently pipe data from a source directly to the client. The true power of this design choice lies in its creation of a unifying API. Node.js must handle many disparate forms of I/O, from files and network sockets to compression algorithms and standard input-output. Without a common interface, connecting these different sources and destinations would require custom, brittle glue code for every pair of interactions. By having all of these components implement the stream interface, Node.js provides a universal protocol. This allows developers to seamlessly connect or pipe a file-read stream into a compression stream and then into an HTTP response stream. Each component in this chain understands the same fundamental language of data flow, events, and back pressure. Thus, streams are not just an efficiency tool, they are a powerful abstraction that fosters composability and code reuse, forming the very backbone of data processing in the Node.js ecosystem. The four pillars of Node.js streams. The Node.js stream module provides four fundamental base classes that serve as the building blocks for all stream-based operations. Understanding the distinct role and data flow of each type is essential for correctly composing data pipelines. Readable streams. A readable stream represents a source from which data can be consumed. Its role is to produce data which flows unidirectionally out of the stream. Common analogies include a water tap that releases a flow of water or a novel being read page by page. In practice, any object that generates data for consumption is a readable stream. Canonical examples include fs.createReadStream for reading files, the request object on an HTTP server that provides the client's incoming data, and process.stdin for reading from standard input. In a TypeScript environment, these are instances of the readable class imported from the stream module. Writable streams. A writable stream represents a destination or sink to which data can be written. Its role is to consume data, which flows unidirectionally into the stream. Analogies include a bucket that collects water or a notebook that you write in. Core examples are fs.createWriteStream for writing to files, the response object on an HTTP server used to send data back to a client, and process.stdout for writing to standard output. These are implemented as instances of the writable class in TypeScript. Duplex streams. A duplex stream is one that is both readable and writable, functioning as a two-way communication channel. Data can flow both into and out of a duplex stream. Crucially, the readable and writable sides of a duplex stream operate independently of one another. The classic example is a TCP socket as implemented by net.socket, which allows for simultaneous sending and receiving of data over a network connection. These are instances of the duplex class. Transform streams. A transform stream is a specialized type of duplex stream where the output is a computed function of the input. Like a duplex stream, it is both readable and writable. However, its two sides are linked. Data written to its writable side is processed and then pushed to its readable side for consumption by the next stream in a pipeline. This makes it an ideal tool for in-flight data modification. Examples include zlib.create.gzip for data compression, crypto streams for encryption, or a custom parser that converts CSV data to JSON. In TypeScript, these are created from the transform class. Stream type primary role, data flow, canonical example. Readable source of data. Outgoing FS create read stream dot writable destination for data. Incoming FS create write stream. Duplex two-way channel. Bidirectional. Independent. Net.socket. Transform in-flight data processor. Bidirectional. Linked. zlib. Create. gzip. Export to sheets. The heart of data consumption. A deep dive into readable streams. To effectively use streams, one must understand the mechanisms that govern how data is consumed from a readable stream. This is controlled by two distinct operational modes, an underlying state machine, and a well-defined set of lifecycle events. The two consumption modes, flowing versus paused. Every readable stream operates in one of two modes, which dictates the control flow of data consumption. Paused mode, the default. By default, a readable stream is created in paused mode. In this state, it will not produce data automatically. The consumer must explicitly request data by calling the stream.read method. This is a pull-based mechanism where the consumer dictates the pace of data transfer. Consumption in this mode is typically handled by listening for the readable event, which fires whenever new data is available in the stream's internal buffer. Inside the event handler, the consumer calls .read repeatedly in a loop until it returns null, signifying that the buffer is currently empty. Flowing mode. In flowing mode, the stream actively pushes data to the consumer as quickly as the underlying resource can provide it. This is a push-based mechanism where the producer dictates the pace. A stream automatically switches from paused to flowing mode under one of three conditions: A data event handler is attached. Stream.onData. The stream.resume method is explicitly called. The stream.pipe method is called to send the data to a writable stream. A stream can be switched back to paused mode by calling stream.pause or by removing all data event listeners and pipe destinations. The underlying state machine, readable flowing. The distinction between flowing and paused modes is an abstraction over an internal property named readable flowing. This property, a detail often explored in technical interviews, represents the true state of the stream's flow. It can have one of three values: null, the initial state of a newly created readable stream before any consumer has been attached. The stream is idle. False, the stream is in what is effectively paused mode. A consumer is attached, but the flow of data is halted. True, the stream is in flowing mode and is actively pushing data to its consumer. In TypeScript, the @types/node package correctly types this property as Boolean pipe null. The event-driven lifecycle, a nuanced look. Since all streams are instances of event emitter, their life cycle is governed by a series of events that signal state changes and data availability. Data, emitted exclusively in flowing mode whenever a chunk of data is ready for consumption. The data chunk, typically a buffer or string, is passed as an argument to the event listener. Readable, emitted in paused mode to signal that there is data in the internal buffer that can be read. The listener receives no data. It is a notification to call stream.read to retrieve the data. End. Emitted. Once there is no more data to be consumed from the source. This event is guaranteed to fire only after all data has been read from the stream. Error. Emitted if an error occurs at any point during stream processing, such as a failure to access an underlying file. This is the primary mechanism for error handling. Close. Emitted when the stream and its underlying resource, e.g., a file descriptor, have been closed. It signifies that no more events will be emitted and no further computation will occur. Not all streams emit this event. Finish. A writable stream-specific event. It is emitted after the stream.end method has been called and all buffered data has been successfully written to the underlying system. The choice between the data, flowing, and readable, paused, consumption models is more than stylistic. It represents a fundamental decision about who controls the data flow. Using onData puts the stream in charge, pushing data reactively. This is simple but can overwhelm a slow consumer. In contrast, using onReadable puts the consumer in charge. It is a proactive, pull-based model where the consumer decides when to request data. This pull model is the foundation of manual flow control, as the consumer can simply stop calling .read to halt the data flow without needing to explicitly call .pause. Therefore, the readable event is the tool for fine-grained consumer-driven control over the stream. Mode behavior, primary event control paradigm. Typical use case, flowing data is pushed automatically. Data producer-driven, push. Simple data transfer, pipe. Paused, data must be pulled manually. Readable, consumer-driven, pull. Fine-grained processing with manual back pressure. Export to sheets, the art of flow control. Mastering back pressure. One of the most critical and nuanced concepts in Node.js streams is back pressure. This is the mechanism that prevents a fast, readable stream, a producer, from overwhelming a slow writable stream, a consumer, with data. Without back pressure, the consumer would be forced to buffer incoming data in memory, which can quickly lead to excessive RAM usage, performance degradation, and ultimately, application crashes. The analogy of pouring water too quickly into a narrow funnel, causing it to overflow, is apt. Back pressure is not an automatic physical limitation, but rather a cooperative feedback loop between the producer and consumer. This protocol is orchestrated by a few key components: the buffer and high watermark. Every writable stream has an internal buffer to temporarily store data chunks it has received, but not yet processed. The high watermark is a constructor option that defines a threshold for this buffer's size. For standard streams, this is measured in bytes, defaulting to 16 kilobytes, while for streams in object mode, it's measured by the number of objects. This property is a threshold, not a hard limit. It's the point at which the stream signals that it is full. The back pressure signal, writable.write, returns false. When a consumer calls writable.write chunk, the method returns a Boolean value. If the internal buffer's size is below the high watermark, it returns true. However, once the buffer's size exceeds the high watermark, the method returns false. This false return is the crucial back pressure signal indicating to the producer that it should stop sending data. In TypeScript, the signature for .writeIn at types/node explicitly shows this Boolean return. Write returns Boolean. The producer's response, pause. A well-behaved producer must respect this signal. Upon receiving false from a write call, the producer must stop writing new data. If it's reading from a readable stream, it should call readable.pause to temporarily halt the flow of incoming data. The all clear signal, drain event. As the writable stream continues its work, it processes the data held in its buffer, causing the buffer's size to decrease. Once the buffer has been sufficiently emptied, i.e., its size drops below the high watermark, the writable stream emits a drain event. This event is the all clear signal, indicating that it is ready to accept more data. Resuming production. Resume. The producer, which has been listening for the drain event, will then call readable.resume to continue the flow of data, and the cycle repeats. It is critical to understand that this mechanism is a protocol, not a physical guarantee. The system relies on the producer to cooperatively listen for and react to the signals from the consumer. If a developer manually writes to a stream and ignores the false return value from .write, the back pressure protocol is broken. Data will continue to be buffered in memory, defeating the purpose of the mechanism and creating a potential memory leak. The Santo stream.pipe method is so valuable because it correctly and automatically implements this entire pause and resume protocol, abstracting away the complexity. When not using pipe, the responsibility to implement this logic falls entirely on the developer. Beyond buffers, the power of object mode. By default, Node.js streams are designed to work with binary data, specifically buffer and string types. However, many real-world applications require processing pipelines that operate on structured data. To accommodate this, streams can be switched into object mode by setting the object mode true option in the stream's constructor. In this mode, a stream can handle any JavaScript value, with the exception of null, which is reserved as a special signal to indicate the end of the stream. This feature is exceptionally powerful for creating complex data processing workflows. For example, a build tool like Gulp uses object mode to pass vinyl file objects, JavaScript objects representing files with metadata and contents, through a series of transform plugins. Another common use case is parsing a large CSV file, where a transform stream converts each text row into a structured JavaScript object, which is then passed down the pipeline for further processing. The most critical consequence of enabling object mode is how it redefines the meaning of the high watermark property. In a standard byte stream, high watermark specifies a threshold in bytes. The default is 16,384, 16 kilobytes. In an object stream, high watermark specifies a threshold in number of objects. The default for this mode is a much smaller value of 16. This change in units has profound implications for memory management. A developer might see the low default high watermark of 16 and assume it implies low memory usage. However, if the objects being streamed are large and complex, this assumption can be dangerously wrong. Consider a pipeline processing database records or file metadata where each object consumes several kilobytes of memory. If back pressure is applied, the stream will buffer up to 16 of these large objects. As demonstrated in a real-world scenario, this can easily lead to memory consumption in the gigabytes, causing the process to crash from memory exhaustion. Therefore, when using object mode, it is not merely an optimization, but a critical necessity to analyze the size of the objects being processed and tune the high watermark accordingly to find a safe balance between throughput and memory footprint. Relying on the default value in a production environment is a significant risk. TypeScript provides invaluable tools for working safely in object mode. By using generics when defining a custom stream class, a developer can enforce type safety throughout the pipeline. For example, class CSV parser extends. Transform clearly defines that the stream expects strings as input and will produce myCSV row object instances as output. This allows the TypeScript compiler to catch errors at compile time and provides excellent auto-completion and clarity for downstream consumers. Building robust data pipelines. Pipe versus pipeline. Connecting streams to form a data processing chain is a cornerstone of their utility. Node.js provides two primary mechanisms for this: the traditional .pipe method and the modern stream .pipeline function. The classic method: source.pipe destination. The .pipe method is a function on the readable stream prototype. It is the classic way to connect a source stream to a destination stream. Its primary function is to automate the reading of data from the source and writing it to the destination, correctly implementing the back pressure protocol to manage flow control. However, .pipe has a critical flaw. It does not handle errors or stream cleanup properly in a multi-stage pipeline, e.g., readable.pipe, transform.pipe writable. If an error occurs in the readable or transform stream, it will not be propagated to the final writable stream's error handler. If the error is unhandled, it will crash the process. Even if handled, the error will not automatically destroy the downstream streams in the chain, leading to resource leaks, such as open file descriptors or dangling network connections. The modern standard, stream.pipeline and stream.promises.pipeline. To address the shortcomings of .pipe, Node.js introduced stream.pipeline. This is a module method that takes a sequence of streams as arguments, followed by a final callback function that is invoked upon completion or failure. It offers several key advantages that make it the recommended best practice for production applications. Centralized error handling. If any stream in the pipeline emits an error, pipeline ensures that the error is forwarded to the final callback. This provides a single, reliable place to handle failures from any stage of the pipeline. Automatic cleanup. Pipeline guarantees that stream.destroy is called on all streams in the pipeline, regardless of whether it completes successfully or fails due to an error. This automatic resource cleanup is crucial for preventing memory and file descriptor leaks. Promise support. The stream/promises module exports a version of pipeline that returns a promise. This allows for clean integration with modern async await syntax, making asynchronous stream code much easier to write and reason about. In an interview setting, the choice to use pipeline over pipe is a strong signal of experience and maturity. It demonstrates an understanding that goes beyond the happy path of simple examples and considers the real-world requirements of robust error handling, the resource management, and application stability. It shows that the developer builds code that is resilient and production-ready, a hallmark of a senior engineer. Crafting custom streams with TypeScript. While Node.js provides many built-in stream implementations, the true power of the stream ecosystem is unlocked when you create your own custom streams to encapsulate specific logic. This is achieved by extending one of the base classes from the stream module, readable, writable, or transform, implementing the internal API. When creating a custom stream, you must implement specific internal methods, which are prefixed with an underscore. These methods are for the implementer to define the stream's behavior and should never be called directly by a consumer of the stream. Read size, required for custom readable streams. This method's job is to fetch data from an underlying source and push it into the stream's internal buffer using this .push chunk. The stream's internal logic will call read when a consumer is ready for more data. To signal that there is no more data to produce, the implementation must call this .push null. Write chunk encoding callback. Required for custom writable streams. This method is responsible for processing a single incoming chunk of data, e.g., writing it to a database. After processing is complete, it must invoke the callback function to signal that it is ready for the next chunk. If an error occurred, it should be passed as the first argument to the callback. Transform chunk encoding callback. The core of a custom transform stream. It receives an input chunk, performs an operation, and can then use this .push to send the transformed data downstream. It is flexible. It can push 0, 1, or many output chunks for each input chunk. It must call the callback to signal that it has finished processing the current input chunk and is ready for the next one. Final callback, or flush callback, an optional method for writable and transform streams that is called just before the stream ends. It is used to flush any remaining buffered data or perform final cleanup operations. The stream will not emit its finish event until this method's callback is invoked. TypeScript's contribution. TypeScript significantly enhances the development of custom streams by providing static type safety. Typed callbacks. TypeScript provides utility types like transform callback, defined as error, null, data, any, bounds void, which ensures that the required callbacks in methods like transform and write are implemented with the correct signature. Typed chunks. In the internal methods, the chunk parameter can be strongly typed. For example, transform, chunk, myDataObject. This is especially powerful when working in object mode, preventing runtime errors and improving code clarity. Class generics. For maximum type safety, a custom class can be defined with generics, such as class myTransform extends transform. This provides end-to-end type checking, ensuring that data flowing into and out of the stream conforms to the expected types, which is a major advantage in complex pipelines. The evolving landscape, Node.js streams versus the Web Streams API. The stream ecosystem is evolving. While Node.js has its own robust, long-standing stream implementation, a modern, standardized API has emerged, the Web Streams API. This API is now available in modern browsers, Deno, and has been integrated into Node.js, creating a new landscape for developers to navigate. The two APIs have fundamentally different designs. The original Node.js streams are built upon the event emitter class, using events open quote, data, close quote, end, open quote, close quote, and callbacks for managing flow control and completion. In contrast, the Web Streams API is promise-based, designed from the ground up to work seamlessly with async/await, offering a more modern and often more ergonomic approach to asynchronous programming. Key conceptual distinctions include error handling. Nodes.pipe has flawed error propagation, which necessitated the creation of stream.pipeline. The Web Streams API's .pipe2 and .pipe-through methods are promise-based, making error handling natural via .catch or a try-catch block with async await. Backpressure. Node.js uses the high watermark and drain event protocol. Web Streams provide a more explicit mechanism with a desired size property on the stream's controller, which gives more precise feedback on the buffer's state. Unique Web Streams. Features. The Web Streams API introduces powerful concepts not native to Node.js streams, such as teeing, .t, a built-in method to split a single readable stream into two identical branches, allowing two consumers to read the same data independently. Locking, .getReader. A web-readable stream can be locked to a single reader, preventing other parts of an application from interfering with its consumption. Cancellation, abort signal. Native support for aborting a stream operation using an abort controller, a standard pattern in modern web development. Recognizing that developers need to work in a world where both APIs exist, the Node.js team has provided crucial interoperability functions. Stream.readable.from-web can convert a web-readable stream, like the response body from a fetch call, into a Node.js readable stream, and stream.writable.to-web does the reverse. An understanding of these two APIs and the bridge between them is a forward-looking skill. It shows an awareness that the JavaScript ecosystem is converging on standards. A developer who can leverage a modern web stream-based library and pipe its output into a legacy Node.js-based system demonstrates adaptability and the ability to work effectively in this evolving hybrid environment. Feature node, JS Streams, Web Streams API. Core paradigm, event emitter and callbacks, promises, and async await. Backpressure. Signal write, returns false, drain event desired size property. Error, propagation manual, pipe, or automatic, pipeline. Built-in, promise rejection. Stream splitting. No built-in support, .t method. Cancellation, manual, custom implementation, native abort signal support. Primary use case, Node.js ecosystem, universal, browser, Deno, Node.js, export to Sheets. Conclusion, synthesizing knowledge for the interview. A deep understanding of Node.js streams is a hallmark of an experienced Node.js developer. The core concepts revolve around using streams for memory and time efficiency by processing data in chunks. This is enabled by the 4 stream types: readable, writable, duplex, and transform, which form a composable system for data pipelines. Mastery requires understanding the backpressure protocol as a cooperative mechanism, recognizing the memory implications of object mode, and preferring the robust error handling and cleanup of stream.pipeline over the traditional .pipe. Finally, awareness of the modern WebStreams API and its relationship with Node's native streams demonstrates a forward-looking perspective. This knowledge can be synthesized to address a complex system design style interview question, such as, you need to process a very large, multi-gigabyte CSV file from a remote SFTP server. Enrich each row with data from a database, and then upload the transformed data as new line delimited JSON to an S3 bucket. How would you design this in Node.js? And what are the key performance and reliability considerations? A strong conceptual answer would outline the following stream-based pipeline. Extraction. Use a streaming SFTP client library to obtain a readable stream of the CSV file. This avoids downloading the entire file to local disk, which would be inefficient. Parsing. Pipe the raw SFTP stream into a transform stream that uses a streaming CSV parser. This parser stream should be configured with object mode, true to emit a structured JavaScript object for each row. Enrichment. Pipe the object stream into a second transform stream. This stream's transform method will be async. For each row object, it will perform an asynchronous lookup to a database to fetch additional data. Once retrieved, it will merge the data into the object and push the enriched object downstream. Concurrency of database lookups should be managed here to avoid overwhelming the database connection pool. Serialization. Pipe the stream of enriched objects into a third transform stream. This stream will take each final object, convert it to a JSON string using json.stringify, and append a new line character \n. This stream effectively transitions the pipeline from object mode back to a standard byte stream. Loading. Pipe the final new line delimited JSON string stream into a writable stream provided by an S3 SDK that supports streaming uploads, multi-part upload. This sends the data directly to S3 without buffering the entire transformed result in memory. Orchestration and reliability. The entire sequence of streams must be wrapped in stream.promises.pipeline. This is non-negotiable for a production-grade solution, as it guarantees that if any stage fails, e.g., the SFTP connection drops, the database lookup fails, or the S3 upload errors out, all other streams in the pipeline are properly destroyed, preventing any resource leaks. Flow control. The use of pipeline automatically handles backpressure. If the S3 upload is slow, it will propagate backpressure up the entire chain, eventually pausing the SFTP read stream. This prevents memory from being exhausted by an accumulation of buffered objects during the database enrichment phase. A sensible high watermark should be explicitly set on the object mode streams to consciously control the in-memory buffer size based on the expected size of the row objects.